All right, can you all hear me? Okay. Before I start talking about the new lab, do you folks have any questions about the multimeter quiz? It's due in a couple days. Questions or concerns? No questions? It's easy lab. Okay. So let me get started then on this new lab. So I am giving you an extraordinary amount of time to write this lab, to do this lab, the lab report for this. So the next lab is on Ohm's law. It is due October 29th. And the reason why is because I want you to turn in a hard copy. From now on, most of the labs that you will be turning in, you're going to be turning in a hard copy of the lab. So if you go on Canvas, you will not be able to upload this lab report. You actually have to print it out and hand it in to me. That allows me to grade it much faster than what's happening right now. I did grade the first lab, and I'm in the process of grading the second one, and I'm hoping I'll get the third one graded soon, so that I'm all kind of caught up. Then of course I have the multimeter quiz. Okay, for sure by the 29th I'll be caught up. Okay. And yeah, I apologize for taking so long to grade your labs. And if you ever have any questions on the lab, email me. I know there's one or two people I haven't responded to yet. I will respond to you regarding the labs. Okay. This lab, like it says in the syllabus, has to be typed. Okay. Somebody in the previous group asked, should this be typed? And my answer is yes. Okay. The lab has to be typed. Okay. So whatever the requirements were in Physics 205, they're pretty much the same here. Everything has to be typed. Graphs have to be made in using graphing software. So I think most of you folks in 205 use Davis. So you can use Davis to do the graphs. And you're going to copy and paste the graphs into your report. Okay. Any questions regarding what I expect from the report? I mean, it's going to be typed up just like you typed it up last semester. And I'll say I'll talk about a few of the requirements regarding the lab as I discuss the experiment. So this is a lab on Ohm's law. It's more of a lab on how to learn how to wire things. There's not a lot of air, there's very little air propagation in this lab. The next lab will have a lot of air propagation, but we will be doing graphs and analyzing graphs. Regarding using other options for making graphs, if you choose to use something other than Davis, the software that you use has to allow you to do a curve fit, give you the curve fitting parameters, the results of the curve fit, along with the uncertainty in the curve fit parameters. And that's the big issue, is that some software They allow you to do a curve fit, but then there's no uncertainties in those curve fit parameters. Okay, so that's why I've been using Cy Davis. The old version of graphical analysis does that too. Yeah, Excel does not, right? So Excel won't do that. That's why I want to avoid using Excel, and that's why I'm using Cy Davis. And I know that I've used Cy Davis. I haven't had a lot of problems with it. The only problem I've had with Cy Davis is on the Mac version. For some reason, it disappears from your computer and you have to reinstall it. Okay. If you have questions on how to use Cy Davis, please contact me. There is a document on Canvas that gives you instructions on how to use Cy Davis. So if you hit 205 here, I think in 205 you use Cy Davis. So I will look into RStudio. Basically, doesn't matter to me what software you use as long as the software gives you the uncertainty in the curve fit parameters. But I will, so that's a good idea. I'll look at the RStudio. And is RStudio free? Okay. So I'll look into that. Thank you. If anybody finds anything else that's out there that's free, let me know. Okay. Because the program we used to use stopped showing the uncertainties in the curve fit parameters, and that's kind of useless to us now. Okay. So this next lab is on Ohm's law. We talked a little bit about Ohm's law a couple of weeks ago, and the lab will allow us to elaborate on it. I will have a lecture where I get into a little bit more theory regarding Ohm's law. That's chapter 27. Granted, that initial discussion on Ohm's law is included in chapter 27, but I want to spend maybe 20 or 25 minutes after we do chapter 26. I'm going to spend 20 or 25 minutes of a lecture talking about some of the basically a model of charge flow in a wire. Okay. So it give you a better understanding, I hope, of what's happening to the electrons in a wire. So there's 4 parts to this lab. And really the goal is to verify Ohm's law, to learn how to calculate electrical resistance, and to measure voltage and current. Learn how to use the multimeter. And we're going to look at something called a diode. We're going to look at its behavior, but we're not going to study in detail. We're only going to use it as an example of a non-ohmic element of a circuit. Okay. Now, the first part of the lab is fairly straightforward. And it has to do with the fact that we're going to be building our circuits on a device called a Protoboard. So you should have one of these in your lab kits. Okay? This is called a Protoboard. Engineers use Protoboard, not this type. This is kind of small. This is a cheap version of it. All right? But they use Protoboards to help design their circuits and to test their circuits. Okay. And so this Protoboard has a bunch of holes in it, and you wire things by basically putting wires or elements into the holes. And I want to get another circuit element, a resistor. Something like this. This is another element that you're going to be learning how to use in a circuit. You just put them in the holes. You got to put them in the right way, though. I'm just doing it randomly, just to show you how they work. Okay. The problem is you need to know how this thing is wired. So underneath there's conductor. Inside here there's conductor. and the holes are connected in a certain way. You need to figure that out. And the question is, how are you going to figure out how the holes are connected? Just let me check the chat real quick. Yeah, I mean, we call them, some folks call them these breadboards too. So how are you going to determine how the holes are connected together? Well, we're going to use the multimeter, and we're going to measure resistance. And so I have the multimeter here. I'm going to set the multimeter to measure resistance, and I'm going to put it on the highest setting right now. Okay, so when it's on the highest setting and there's no connection that says 1 with a dot after it, that means the resistance is too high for that scale. I'm on the 20 megohm scale, so it's too high. Basically, it means that you have no connection. If I connect these together, like this, then the resistance will be 0. And no matter what scale I use, it'll read 0 or close to 0. Okay, that 0.14 is because of either issues with the contacts or the resistance of the wires. Okay, so what you're going to do is you're going to put 2 wires in random holes. You're going to connect the multimeter to each of the wires, like you see here. And you're going to read the resistance. And it's obvious that they're not connected, those holes. But there's other pairs of holes that will be connected. So let me change to a different pair, such as these. And you see the multimeter reads 0. So those 2 holes are connected. What other pairs are connected? And so what you would do then is take one of these and move it to another set of holes and see if they're still connected. Are all the ones on that line, along that line near the red plus, connected to each other? That's one thing you want to check. Okay? And so what you're going to do is you want to see how all these holes are connected. Now granted, there's a pattern, so you do not have to go through every single pair of holes to check if they're wired. You'll see a pattern, and the pattern will be pretty straightforward. Then what you're going to do, let me scroll down. And go to this figure. It's almost like your Protoboard. This is the one we use. This is the that picture is a picture of our Protoboard we use when you're on campus, or a breadboard, whatever you want to call it. All you're going to do is use the drawing tools in Word. You're going to draw lines showing how they're connected. Okay, you should use the drawing tools. It's easier. You just draw lines to show me how they're connected. Just give me enough of a pattern so that I know that you understand how they're connected. Whatever you're communicating, you got to communicate to the reader, either me or a student in class, that you know how everything's connected there. Because you're really writing not to yourself, but to someone in the class. Okay. Someone at your level. And so you need to show that you understand how this thing is wired. Questions on that? And one of the things about this, the multimeter, is it gives you an idea that you can use this as a diagnostic tool. So for example, let's say you plug something in and all of a sudden it stops working and you suspect the plug, or your wire, your cable that goes to your electronic device. Okay. One of the things you can do to test is to measure the resistance between the two prongs. If the resistance is 0, something is shorted. Something is wrong with your plug. If the resistance between these two guys, because they're connected to different wires, if the resistance between these two wires is 0, something is shorted, something's wrong. Okay? Or any two pairs. Okay? Any two pairs on here, as long as it's 0, there's probably something wrong. Okay? Unless it's designed so that they're connected. Okay. So you can use resistance to diagnose things. So if you have a cable and you're not sure that one end of the cable is continuous with the other end, you can also connect a multimeter to this prong and then a multimeter on the other side of the cable to the same prong. If you get 0 ohms, then you know that those are connected. If you get OL, that means you know they're not connected. So you can use the multimeter as a diagnostic tool. In the old days, the Christmas tree lights were all connected in series. So if one of the bulbs went out, everything went out. And what one would have to do if they didn't have a multimeter was they would have to take another bulb that they knew worked, hopefully it worked, and they'd have to replace the new bulb. You'd have to go one by one and replace the bulbs in the set of lights with the one that works and see which one is dead. Okay, so if you replace a bulb with your working one and all the lights go on, that means you know that that bulb is dead. Well, what you can do, instead of using a bulb, you can use a multimeter and just measure the resistance of each bulb. If the resistance of one of the bulbs says OL is too high, then you know that that bulb is dead. You're going to end up with 2 of these very soon because you need another multimeter. In fact, it would be very advantageous to get the second multimeter as soon as you can. So I'll be here on Monday. If you don't pick up your multimeter on Monday, when you take your test next Friday, I'm going to hand them out. So one way or other, you're going to get a second multimeter. But let's say you have 2 multimeters. One of the multimeters stops working. You suspect the fuse. You take the fuse out, and with your second multimeter, you measure the resistance of that fuse. If the fuse resistance is 0 or close to 0, then you know the fuse is okay. If it's too high, then you know something's wrong with the fuse. So you can use this as a diagnostic tool. And one of the things, one of the important skills I want you to develop in this course is troubleshooting skills. It's one of the most important skills you will have as an engineer, a chemist, biologist, computer scientist, anything that involves science, anything that has the word science in it. Okay, even as a computer scientist, because computer science folks, they write code. Code doesn't work, they have to troubleshoot it. They have to think about. They have to develop a process to figure out where has their code gone wrong. Okay. Troubleshooting is a very important skill. It's really it's not emphasized a lot, but I do emphasize it. And you saw it when you built the electroscope and electrophorus. The idea of building it was easy, but then making it work was another issue. Okay, so one of the things as an engineer you have to do is you have to learn how to make things work. You have to figure out what's wrong. Right? You can't look that kind of stuff up. Okay, there's no answer you can look up. You have to actually go through and one step at a time and figure out what's wrong with your device. It's an important skill. And so later on this semester, you're going to build a motor for me, and you're going to spend a lot of time troubleshooting it to make it work right. It's an important skill. You need to develop it. Okay. So I do emphasize that this device can be used not only to measure things, but also to find out what's wrong with things. Okay. In this case, with electrical circuits. Questions? Okay. So that was part one. Part one's straightforward. And then every circuit that you're going to build in this lab, you're going to build on this board. Okay. Part two, we're going to test Ohm's law. You're going to build a very simple circuit and test Ohm's law. So remember what's Ohm's law? R is delta V over I. The resistance is delta V over I. And if something obeys Ohm's law, this value is the same independent of the applied voltage. In other words, if you plot delta V versus I, and I know I'm plotting it different from the PowerPoint notes, and I'm doing this on purpose. If you plot this and you get a straight line, that means this is a constant independent of delta V, then that material obeys Ohm's law. Okay. If you have a material that doesn't obey Ohm's law, it doesn't necessarily mean that you can't use this equation. A light bulb doesn't obey Ohm's law, but you can still calculate the resistance at a particular applied voltage. That's still applicable, okay? All right, so we're going to build a simple circuit. You're going to have a power supply whose voltage you can vary. That's why I drew the arrow. You're going to take a wire, connect it to one side of a resistor. A resistor is just, and I'll tell you what a resistor is in a minute, what it's used for. Then the other side of the resistor is going to go to the ammeter. And then the other side of the ammeter, the common side of the ammeter, will go to the negative side of the power supply. So that's your circuit. And then you're also going to put a voltmeter. You're going to measure the voltage. Across the resistor. And this resistor is 820 ohms. You have to use that value. That's one of the indications that you did the lab, is that you use that value. Okay, I had a student last semester who did not use the value that I designated, and I can't tell if that person fudged the data or not. So I hammered that student, okay, on their lab report grade, okay, because I don't know if that data was fudged. The data, in fact, the data didn't even make sense. This lab is very important, even though it's pretty basic. It's very important because it helps you to learn how to wire circuits. Okay, so you need to go through the process of learning how to wire the circuits. Because when you come out to campus, we're going to have labs where you're going to have to wire the circuits while you're here. Okay. And when you take Engineering 17, you have to know how to wire your circuits. I mean, you're going to have a Protoboard that's completely full of wires when you take that course. Okay, so you have to be good at wiring circuits. Okay, so you want to use this lab to develop your skills. So you're going to be measuring voltage as a function of current. And the reason why I want you to plot it this way instead of I versus V is because, since delta V is I times R, the slope of this is the resistance. If you plot it the other way, then the slope is 1 over the resistance. Okay? So you're gonna take 7 data points, because that's all you can take. That's because of our power supply. Let me show you the power supply. Power supply is this thing. This is in your kit. Okay. So you should have had I don't know if you took it out of the box. I actually took out one of the kits because I wanted to see what your kit looks like this semester. And the power supply is not in the box. So he actually took it out of the box. So it looks like this. Okay. And by the way, if you go on Canvas, Tyler actually created a video for this lab to help you to do this lab. So you should watch the video. Okay. Well, you better watch the video because otherwise you're going to have a hard time with the lab. This is the power supply, and we can vary the voltage of the power supply by turning the screw. There's only 7 settings. And there is if you don't have a screwdriver, I think, but although a flathead screwdriver, we have in here, let me find it. There's a little device that comes with the kit. Looks like this. That allows you to change the voltage. Okay. So basically, sorry. Put this in here. Like so. And then you just turn it. Okay. That's how you change the voltage. So it's this little thing it's in the bag. It should come in the bag. Now it could be that your kit has the original power supply in the box. I think this one is not in the original box because this is a used one that one of our students used in the previous semesters. So, in order for you to do the wiring, let me show you what I did. Now, granted, this is not the Protoboard you're using, but I actually taped part of it onto the Protoboard. So this comes with your kit. It has a green end. And then you can screw in. You can put some screws in and then use the screws to tighten them so that the wires stay in. So you put some wires in here. You have wires in your kit. Okay. You put the wires on each one of these, one on each side, and then you use a screwdriver to tighten it so they stay in place, like these guys. And then this connects to the green thing. So basically, all I have to do is this. So I taped it. You do have electrical tape that comes with your kit. Okay, and I did this because this thing then it stays in place. So that's one idea you can use to make your wiring easier. Okay. In your case, you would have to tape it to this thing, like so. If you want to know how the wires are connected to this, because those two wires are either connected to the center pin or to the outside conductor. Just use a multimeter, connect the multimeter, one end of the multimeter here, for example, and the other end to the center pin. If you get 0 ohms, that means you know they're connected together. That's your high voltage. Okay. Questions? No questions? Okay. So that's your power supply. It's kind of clunky, okay, because you have to use the little device to change this. It's not a real power supply where you have just a dial. But they worked okay for us. So you'll have 7 data points. And you do a curve fit. Do it in Davis, let's say. Again, any software that gives you the parameters, the curve fit parameters, and their uncertainties. If you did not take this course at Sierra College, I kind of need to talk to you. Okay, if you did not take Physics 205 at Sierra College, I probably need to talk to you. All right. Now, this is a line inside Davis, and in most graphing software, you actually have two options to fit to a line. Right? One of them is a bad option. One of them is a really bad option. Which one is it? Anybody want to guess as to which one's the bad option? Well, I'll tell you, this one's the bad option. Never, ever fit to this. Okay? Don't ever fit to that. That's actually a bad choice. Because you're forcing the graph to go through the origin. What if something isn't calibrated correctly? That'll show up here. So never, ever use this to do a curve fit unless you know for sure that the data has to go through the origin. Okay? You're forcing the data to go through the origin if you use that graph. So never use this. Okay? Just don't use this. Use this. So your software is going to give you M plus or minus delta M, B plus or minus delta B. I need to see this on the graph. In fact, the raw values have to be shown on the graph. Why? Because when you get to the results section, I want to see that you can take this number and report it to the correct number of decimal places. I need to be able to see that you know what you're doing. If you don't have this here, I will automatically deduct points. I'm a pretty harsh grader on the written labs, okay? So you want to do a good job. You can ask anybody who's had physics with me that I'm a pretty harsh grader on the lab reports. And so I need to see this. Okay? This has got to be on the graph. That way, when later on in the lab where it says report the slope and you're going to report it to the correct number of decimal places, I'm just going to compare this number to what you have written later on, and if you did it correctly, then you're fine. If I don't see anything here, then I don't know if you know how to interpret your results. You will lose points. Okay? Although even though I say that, I still get students who don't do that, so. But I have to say it anyway. Questions on that? Or concerns? So when you go to part, let me show you the lab. Let me show that part of the lab. Hold on a second. In fact, let me do that and then scroll down. I hope nothing freezes. This is part 2 of the lab. There's your data table. Watch the units. Please watch the units. So some students forget about the units here. And if, you know, the funny thing about it is, you know, they'll put down, they'll change this to amps, and then they'll write down like 200 amps. Your wires would melt at 200 amps, okay? And I'll write that down in your lab report. Let's go to the end here, where it says results. Okay, so here it says slope and uncertainty. You want to report your results to the correct number of sig figs. Here it says show your work. Use the equation editor to type in your equation that shows the work. Okay. I want you to show the work because people make mistakes. You know, If I knew that nobody would make a mistake, then I wouldn't have you show your work. Okay, 1 second. I can't find my cursor. All right, let me go back. I'm going to go back up here real quick. Let me make the screen smaller. How do you know this resistor is 820 ohms? Well, each resistor has a color code on it. Just 1 second. Okay, each resistor has a color code on it. So let me grab one of the resistors. It's not going to be the one you're going to be using. This is a resistor. You might say, well, what the heck is that for? Hold on, I got to put on the autofocus. You notice there's stripes on there? That's the color code for the resistor. What are these resistors used for? Well, they're used to limit current in a circuit, or they're used to give you a voltage that you need for a circuit. And we're going to learn more about that when we start analyzing circuits in the next unit. Okay? So, the color code. All the resistors that we're using have, in this course, have 4 bands. 3 of them are used to indicate the value of the resistor. The 4th band represents how accurate, how precise that value is. Okay, actually how accurate it is. So let me write on the board all the colors that are used on the stripes for the resistor to indicate the resistance value. These are the colors: black, brown, red, orange, green, yellow, violet, blue, violet, gray, and white. Okay, so black, 0. Brown is 1, 2, 3, 4, 5, 6, 7, 8, 9. And you see that in that table. That table is in your lab. Now suppose I have a resistor whose value is given by the following. So let me draw a resistor. By the way, these resistors are generally made out of carbon, or they're wire wound, just a long wire. Those, the ones that are made with their long wires, are pretty precise. Let's pretend that we have a resistor where the first band is red, the second band is red, the third band is green. Now the fourth band is either silver or gold. If the fourth band is gold, that means that this value is known to within 5%. If it's silver, this value is known to within 10%. Okay, I don't have a gold marker and I don't have a silver marker, so I'm not going to draw the fourth band. All right, so each one of these, this first one is the first digit, the second one is the second digit, and the third one is the multiplier. The exponent is this color. So the first one's red, 2. The second one's red, 2. And then this one's green, 5. 22 times 10 to the fifth ohms. That's the value of that resistor. So in your case, if you're using 820 ohms, then the first color on your resistor has got to be gray. That's how you're going to identify it. Okay? I'm not telling you anything else. You have to figure that out. Because I want you to learn how to use that color code. Because the other way is to measure the resistance of every single resistor in your toolkit if you want to do that, but that's going to waste a lot of time. Okay? Oh, okay, sorry about that. I have it backwards. I have it backwards, sorry. It's R-O-Y. I go by Roy G. Biv, so I don't know why I got those backwards. Thank you. Yeah, so one way to remember is the colors of the rainbow. Roy G. Biv. BV. Actually, for the rainbow, there's a indigo in here, so BIV, but that's okay. Okay? Thanks for pointing that out. And so you'll identify the resistors. You have to use that value. Anything else, you're going to get hammered on the lab report. Okay? And I know there's only 4 of you here, so I'm hoping that the other folks watch this video, because if they use the wrong they use the wrong resistor, they're going to get hammered on it. All right. Questions? Okay. For part 3, it's very similar to this, except that you're going to replace the resistor with a bulb. Now the bulbs that you use for the multimeter quiz will not work for this lab. I tried it and I just smoked the bulbs when I went to like 6 volts. Just burned them. Okay, so they're not very tolerant. They don't go up to very high voltages. Okay, even 6 volts killed them. And so I had to find something that would work based on the voltages we were given. And so I found a landscaping bulb. These are landscaping bulbs. So you should have one of these. They should come in a box, I think, with your kit. Okay, unless it's one that's been used before. Well, this kit I couldn't find the bulb. So I'm hoping that you have the landscaping bulb. If not, you have to come get one. This kit that I opened up this morning did not have the landscaping bulb. So the bulb looks like this, and it has 2 prongs on it. Okay? So you're going to go through the same process, collect 7 pairs of data, because you only have 7 settings on that power supply. But your graph is not going to be linear, because the bulb does not obey Ohm's law. The graph will have some sort of function. Kind of like that. I don't know what the function is, actually. And even if I did know, I wouldn't tell you. What I want you to do is, I want you to collect the data, plot the data, and find the function that best fits your data. And you have a lot of options to fit your data. I mean, you can try this function. You can try and you can actually define your own functions in SciMath. Okay, you don't have to use the ones that are listed. You can define these if you want to. You can try those are all good ones you want to try. Notice. What do you notice about those equations? There's only 3 curve fitting parameters in each one of those equations. You should use probably no more than 3 curve fitting parameters. I mean, in reality, I can fit the data to a 94th degree polynomial and I get great results. But then if I have a 94th degree polynomial, I have 95 fitting parameters. How do I interpret them? How am I going to interpret them? Right? So even though the curve is fantastic, I have no idea what the heck it means. The less curve fitting parameters you have, probably the better a chance you have of interpreting your results. So what you should do is try these different curve fits and let me know which one worked best. And you can be creative. You can find a different curve fit. You can show all the curve fits that you tried. That's fine too. I mean, that's probably the best thing to do. And by the way, when you with your graphs, make sure you copy and paste your graphs into the report. Okay? Generally, it'll say copy and paste here. That means copy and paste it. Don't put it at the end of the lab report because that's very annoying to me. Because then I have to go between pages all the time when I'm grading the lab report. It should be copy and pasted where it belongs. Okay. Questions on this? Now, let me scroll down in the lab. Let me find my cursor first. So here's part 3 of the light bulb. You only get 7 data points. You do get to measure the resistance of the bulb before and after the measurements. And so in part 3, supposed to write your conclusions. And really all I'm asking for in part 3 is, what is your interpretation of the results? Just try. I don't expect a correct answer. I just want to see you try. Okay. So notice here when in the instructions, it says paste your graph and caption in part 3 of the results section. So paste the graphs where it tells you to paste them. Just follow the instructions. Okay. So let me say a couple of things about the graphs. Well, let me say one thing about the graph, and then let me move this to part 4. Question is, you're making these graphs. What's the purpose of the graph? What's the purpose of creating a graph? Well, the purpose of creating the graph is to organize your data in a visual way. But what's the purpose of the graph if you don't do anything with it in your lab report? That's one of the complaints we get, from like engineering instructors. Students make a graph and they don't use it. They don't do anything with it. Well, then what the heck's it good for? And so what I make you folks do in your lab report is to write a figure caption explaining your graph. So the first sentence should say, well, you plotted and then the second and third say, basically say, okay, I fit my data to this function and the results agree, my data fits the function well, or my data fits the function poorly. And then, what results did you get out of it? If you did a curve fit and you were able to extract a number from it, tell me what you extracted from it. Okay. I don't want a long paragraph. I just want an indication that you try to interpret the graph, and I want you to show me what you learned from the graph. If you don't say anything, you didn't learn anything, and you lose points. Okay? I am critical in grading the lab site. I do look for that. If you just say, this is a graph of voltage versus current, I say, okay, who cares? Give me some more information. What did you learn? That just tells me you learned nothing. All right? Because the graphs serve a purpose. They're supposed to teach you something, and I want to see what you learn from it. Okay? So every figure will have a caption in this course. Now, you'll be happy to know that the next lab, the lab that you do on DC circuit analysis, there's no graphs you have to make. But you do have to do a lot of error propagation. A lot. Okay? All right. And the next thing is, for the first two parts of the lab, you can get away with doing the experiment with just one multimeter, because what you can do is put the multimeter in the circuit, then take it out and then measure voltage. So you can get away for parts 2 and part 3 for using one multimeter. You cannot for part 4. So I'm going to make the multimeters, the second multimeter, available. They came in late. That's why you don't have the second multimeter. I'm going to make the multimeter available starting next week. So on Monday, if you come to campus, I can give you the second multimeter. If not, you will get it on the day of the exam on Friday. Okay, so next Friday, we're going to hand out the multimeters. But if you want to get it ahead of time and you want to work in this lab ahead of time, then by all means, come Monday, I'll give it to you. Now, don't be deceived by the fact that this is due October 29th. On October 15th, I'm going to talk about the next lab. So you really should get this lab done within the next couple of weeks. Okay? Because when I introduce the next lab, it's going to be due the week after this. And that lab is really long. Okay? You have to do a tremendous amount of error propagation, more than probably you've ever done, you ever did in Physics 205. Okay, so I'm warning you now that you have to use your time properly. If you just procrastinate and just wait till the end, you're going to be in big trouble. All right? So use your time wisely. All right, so let's talk about the last part of the lab, part 4, where you're going to be building probably the most complicated lab circuit that you have built this semester. And it's going to require you using a diode. Okay? You're going to be using a diode. A diode is a device that doesn't obey Ohm's law, just like the light bulb. Okay? And I'll probably say more about the diode, not next week, because we have an exam next week, but the following week. when we meet again. I'll say a few more things. I'll just say some real basic things here. A diode is a device that only allows charge to flow in a circuit in one direction. What does the diode look like in your lab kit? Let me turn on the auto focus. Hopefully the camera will start to focus soon. That's the diode. Okay, this is in your kit. Let me see if I can get it closer. And it's not focusing very well. Okay, so it has a little bit of an orange spot on it and a black band. This is the diode. It's tiny. Right. You're going to use this in your circuit. The schematic symbol for the diode looks like this. Triangle with a line on it. And this tells you the direction the currents, the charge will flow. So if you put a positive voltage here and a negative voltage here, higher here, lower here, current will go this way. If you reverse the lead, this is designed so that no current flows. Okay, but it's not really zero. It's a small number, but it's not really zero. Okay, it's actually a very small amount of current will go through there, sub microamps. Okay, but it's essentially zero. When this thing is fully conducting, depending on the diode, the voltage across it, the potential difference across it, the PD across it, will be in the range of 0.2 to 0.8 volts. And that depends on the diode. Some diodes, when this thing is fully conducting, will have a PD of 0.8 volts. Some will be as low as 0.2 volts. And this thing will only allow charge to flow in one direction. The semiconductor device, it has a lot of applications in real life. You can build a very simple digital logic circuit with this. You can also use a more robust one to protect your devices, a motor, for example, from an inductive load. Like when you turn off a motor real quick, you get actually a large current generated. And you don't want it to go through the motor, you make it go through the diode. Okay, and it'll be kind of an industrial diode for that purpose. Okay. Okay, so you're going to be using a diode, but you're also going to be using another device called a potentiometer. So let's talk about wiring the circuit. You're going to have a 12-volt power supply. In other words, you're going to set your adapter to 12 volts. So you're going to connect one end of the power supply to 330 ohm resistor. And this is where we connect to the potentiometer. The potentiometer is basically a resistor. It's a resistor whose value you can vary. In your kit, it looks like this. It has 3 prongs on it. I bent one of them. And it has a dial on it. You can turn a dial. Okay. That dial allows you to vary the resistance from 0 to 1,000 ohms. There's other types of potentiometers that will allow you to vary it from 0 to 100,000 ohms. There are those where you only need to make one full turn. There are those where this thing, you have to turn it 10 times before you reach the maximum or minimum amount. So these have 3 terminals on it, 3 connectors, 3 things to make a connection with. So I'm going to draw kind of a picture. And I'm going to draw the 3 connectors. Okay. And then these go inside the device. If you take a power supply and connect to the outer terminals like that, then you get the full 1,000 ohms. You get the full 1,000 ohms no matter how many times you twist the knob. It's always going to read 1,000 ohms. Okay, so this device will always read 1,000 ohms no matter how you twist it. Okay. If you move this wire to here, you use these two only, this will allow you to vary the resistance from 0 to 1,000 ohms by turning the knob. So you actually now have a resistor you can vary. If you put a multimeter in your circuit, you can measure, you can see the current change as you change this, as you rotate the potentiometer. If you connect your battery to these two, then you have a a resistance that changes as you measure, as you change the dial. It'll go from 1,000 to 0. If these two go up as you rotate clockwise, then these two will go down as you rotate clockwise. Clockwise meaning assuming you're facing it, you're facing that, okay. So you're going to be using every terminal of this potentiometer. People abbreviate it, just call it a pot. It's a 1K pot. That's the term they use. So let me draw the 1K pot like that. So you're going to have this guy here, this guy over here, then the middle one will go to an ammeter. The other side of the ammeter will go to your diode. And then this goes to your common. Then you're also going to measure the voltage across this thing. You have a voltmeter here, like so. You're going to measure the voltage across the diode and the current through the diode. And you need both meters. You need both meters to make the measurements. And the reason why is because you're going to be taking about 26 to 28 measurements. And for you to take this out and move it here and back and forth, it'd be very cumbersome and annoying for you. So I don't want you to do that. So you need the second multimeter to make this measurement or to do this part of the experiment. Okay? Let me show you the data table. And again, in the data table, always watch the units. So let me scroll, see if I can scroll down real quick. There's the data table. The more data you collect, the better. You want to be close to 28 data points, as close as you can. Like I said, the voltage here is going to be very small. If you plot it, your plot will look like this. And in fact, we're going to plot, in this case, we're going to put I on the y-axis and delta V across the diode on the x-axis. So we're plotting current versus potential difference. Right? When you say current, when you say current versus potential difference, the first thing is on the y-axis. And your graph will look like this. And it's an exponential increase. This thing increases exponentially. Okay? And you're going to do a curve fit to this function. You're going to actually have to define it within, you have to actually define it within, you define your own within Cy Davis. Now V sub t, and I want to make sure you can see everything. Let me do this real quick. V sub t is k sub b times t over q sub e. Now in the lab, this is written as delta v. This is written as v. It really should be delta v. We've had that mistake for years. This is the voltage across the diode. So that's your dependent variable, and this is the dependent variable. And this is a curve fit parameter. So k sub b is called Boltzmann's constant. And you might have seen this if you've had physics 215 or if you've had chemistry. So k sub b is 1.38 times 10 to the minus 23rd joules per Kelvin. T is the temperature in Kelvin, and Q is the charge of the magnitude of the charge of the electron. How are you going to know the temperature? Because there's no thermometer in your kit. How are you going to know the temperature? Well, where you live, you have a thermostat, right? The thermostat should tell you the temperature of the room. Of course, it's going to give it to you in Fahrenheit. The temperature in Kelvin, by the way, is 273.15 plus the temperature in Celsius. If you don't have a thermometer in where you live, then you can use a thermostat reading. Okay? Then you'll get the temperature. You got to convert that to Celsius, and then from Celsius to Kelvin, and you will put it in here. This is the diode voltage, and this is a curve fit parameter. Theoretically, it's a number like 1 or 2, but it's really, in practice, it's a number that's between 1 and 2. Okay. Now, if you're going to get a good fit to your data, this is a tough equation to fit to. You actually have to get a good fit around the part that changes the most, the curve part. So you got to collect a tremendous amount of data in this region where it curves the most. Not here, who cares, because it doesn't vary. I mean, it's pretty much almost straight. You want to pin this down. You can pin this down, you get a good results to your curve fit. Okay? And again, your curve fit parameters will be this guy, this guy. And by the way, as you're making the measurements, make sure you're always on the same current scale. Because if you're not on the same current scale, you're going to be changing the resistance of your circuit. Because the resistance of the ammeter changes when you change scale. And that'll throw off your results. It'll make your graph discontinuous. Okay? So before you actually collect data, you should vary the potentiometer and watch how these numbers change. You should vary it slowly. I wish that the potentiometer was 10 turns, but they're very expensive. So we have a cheap 1-turn potentiometer. So when you vary it, you'll notice that at some point, this will change by a great amount for a really small change. In fact, this will change by 0.01 volts, and this will double. And it is in that region where you want to collect a lot of data points so you can pin this part of the graph down. That way you'll get a good curve fit. So you're going to have to tweak this thing just a little bit. So this changes maybe by 0.01 volts, and this will have a big change in current. Okay? When you get to the point where V doesn't change much, then you know you're at this asymptotic point. So you want to collect a lot of data points when it just turns on. Watch when it first turns on. What does that mean when it turns on? Find the point where you start getting current, measurable current. From that point on, you want to collect a lot of data points, and you want to take very small increments in current, in voltage, sorry. How small? Well, I'm going to let you figure that out, because it varies by diode. And so you'll make little tweaks. You just touch the potentiometer just a little bit, and it'll change the voltage by 0.01 volts. How much does the current change by? So you actually got to play around with it first before you collect the data, because it's a very sensitive measurement. You can't just do things quickly. Questions on this? Okay, so in 2 weeks, I'll say a little bit more about the lab. I'll ask you questions about where you're at on the lab. By the 5th, that'll be the week of the 15th. You should be pretty far along on the lab by then, because on the 15th, I'm going to talk about the next lab, and that lab is long. And really what I should say is the report is long. The actual process of collecting data is short, but the process of analyzing data is quite long. Okay, so you do want to get a jump on this. And this is really not the lab report is not hard. Okay, this part is going to be hard for you because of the wiring. But again, because I'm going to be here on Fridays to discuss the lab on most Fridays. I don't know if I'm going to. There might be a time where I teach from home. I'll be here on Mondays. You can bring your lab here, and I can help you with it. That's going to be a huge advantage to you guys. The fact that I'm here to help you with the lab. Because the previous 2 semesters, I wasn't around to help, and students really struggled. Okay? So take advantage of it. Do it right away. Collect the data and write it up soon. All right, then you'll be in a good position for the next lab. So I'm hoping by the 15th, you've collected the data and you're well on your way to write the report. Because starting on the 15th, I'll introduce the new lab. Questions or concerns? All right, so I'm going to stop here then. You folks have a great weekend.